on A we have defined. Similarly, for when the machine is in start state S, on receiving input symbol B, we make a transition to state T. So the same concept or the same transition is defined with respect to its equivalent production. So S tends to BT, and finally we have when we have to replace or when we have to substitute the non-terminals, we can define these two productions, that is capital T tends to AS because we have a transition defined back to capital S. Okay. So the main point or the whole objective here is whenever we have some non-terminals, either capital S or capital T, when we start derivation or when we start substituting the rules or the productions of the grammar, okay, step by step, then we have to finally see to it that all the non-terminals will be derived to some terminals only. This is very important. Otherwise, finally, we cannot derive the string which belongs to the language. So, S tends to epsilon, S tends to AT, and S tends to BT. So, now you can see here, if we replace S tends to epsilon, then definitely this S, when it is substituted, this S will be replaced by epsilon, or it could be replaced by S tends to AT. So, we can see that capital S is leading to set of terminals in the derivation process. Similarly, we have to define its equivalent production for capital T as well. So, you can see here, if we only define the productions capital T tends to AS and capital T tends to BS, then it becomes like a recursive call or a recursive function, because I can always substitute whenever I encounter capital T with either AS or capital T with BS if I don't define these two transitions. Okay. So, we finally at the end of the derivation process, we can see a string comprising of not only set of terminals but also some non-terminals as well, which is not acceptable. So, that is the reason defining these two productions, that is T tends to A and T tends to B, is very important, because it helps us in the derivation of the legitimate or acceptable strings which belongs to the language. So, these two productions are important. So, finally, we can see that there are two non-terminals, capital S and capital T. Capital S is also having one production which leads to what? Set of terminals, that is epsilon, and similarly capital T also leads to some of the terminals. So, this is a valid regular grammar for the given regular language, where the language is defined as set of strings which belong to A comma B star, such that the length of the string is even. So, we will just take one particular example. I will take a string of length even, definitely, because it should belong to the language. I will take A, B, A and B. So, let me check whether for the given string W is equal to AB, AB, the defined grammar, regular grammar, will I be able to derive the string. So, I will just start with the first production. So, capital S is the start symbol of the grammar. So, you can see here, for the start symbol of the grammar, we have three productions. So, S tends to epsilon, S tends to AT and S tends to BT. So, looking at the sequence of the string, so I can take the first production as, this is the derivation symbol, S derives to, I can write AT, okay. So, now in each and every step I have to substitute or I have to replace its equivalent production for the given or for the obtained non-terminal. So, the next non-terminal what I witness here is capital T. So, for capital T, since, so now A is completed. So, now I will substitute the production for T. So, now for capital T, since the second string is B, so I can take it as, I will take this particular production, T tends to B followed by capital S. Okay. So, we have got two terminals and one non-terminal. So, I will continue the process of derivation. So, now again I will retain AB as it is. For capital S, I will consider, since the next string is A, I will take this particular production, S tends to AT. So now I will write A followed by T. So few of the authors, they follow this particular convention. In the bracket, they mention which production, or which rule, R1, R2, R3. So if I sequentially number each of the rules, then I can mention by using which rule or which production, I have obtained this particular derivation. So similarly, AB, AT. So next, I have got one more non-terminal, that is capital T. So now, finally, I need to obtain only one T. So I will make use of this particular production, that is T tends to B, and finally stop the derivation process. So you can see here at the end of the derivation process, the set of strings what I have obtained comprises of only set of terminals, no non-terminal exist. Okay, and this string, which is W, it belongs to language. So this was a simple example. Yeah. So moving further, now as I was mentioning the correspondence between the regular languages and regular grammar, we have one well-known theorem as well. So the class of languages that can be defined with regular grammar is exactly the regular language. So now there is a correspondence between the regular language and the regular grammar. Okay. So this is a theorem. So whenever we have a regular grammar, we can define the regular language, and vice versa also holds good. So we will see how this particular theorem can be considered. So this is the algorithm. So this is the regular grammar, conversion of regular grammar to the finite state machine. So these are the steps to be followed. So we can see here grammar to FSM. Okay. So the input is a regular grammar. So for a given regular grammar, we have to construct or we have to design its equivalent finite state machine. And now we are familiar with respect to the definition of the grammar. So G is equal to V sigma R and S. So the first step indicates that create in M a separate state for each non-terminal in B. So now the finite state machine, so we are all familiar, the finite state machine is defined as capital M is equal to, it has quintuple, that is 5 entities, it has capital K, sigma, capital A, capital S and delta. So these are the 5 entities where capital K is a set of finite states, sigma is again the input alphabet symbols, capital A is the set of accepting states. Since we can have more than one accepting states, always capital A will be a subset of capital K, and S is the start state, and since there is only one starting point or the reference point to read or to start reading the particular machine, S is always 1. So S belongs to K definitely, and delta is the transition function. So keeping this in line, create in M. Okay, so in a particular in M, that is machine, finite state machine, we have to create a separate state for each non-terminal in B. So where how many our non-terminals are defined in capital V, we have to create each non-terminal as one of the dedicated state for the equivalent machine M. So that is the step 1. Next step is start state is the starts corresponding to S. So start state of the regular grammar S will definitely be the start state of the machine as well, or the start state of the finite state machine. So the next step is, if there are any rules in R of the form, this is very important, because now we have to define transitions based on the productions given in the regular grammar. So we have to look for only rules defined in the grammar in order to derive or conclude what is the correct transition to be introduced in the finite state machine. So if there are any rules in capital R of the form x tends to W, for some W which belongs to sigma, that is input symbol. So W is nothing but set of strings. So create a new state labeled hash, that is final. So this is important. So the meaning of step 3 is only that in order to recognize that any one string, which belongs to language, and when we say that a given string should belong to language, definitely that can be recognized or identified in finite state machine only when the machine halts in the final state. So when we have this kind of production, so definitely it is very clear and it is very obvious that we need to create one new state and we can label it as hash. So here hash is just the author convention to indicate that it is a final state. So this is a step 3. Next step is, for each rule of the form x tends to w, y, add a transition from x to y labeled w. Now in the previous slide we just saw that this particular rule or the production is valid. Why it's valid? Because the LHS comprises of exactly one non-terminal and the RHS comprises of one terminal followed by one non-terminal, which is completely legal and valid with respect to the definition of regular grammar. So whenever we have such kind of productions or the rules in the regular grammar, the simple thing or its equivalent transition or its equivalent step in the finite state machine would be adding a corresponding transition from, since capital X and capital Y both are non-terminals, we would have defined separate state well in advance in step 1 already. So we have to only connect those states which are defined in step 1 over the transition, and the input symbol will be W, labeled as W. So for example, if I have S tends to small a and then capital B, this means that I need to have two states. S is one state and B is another state, and since it's a non-terminal, so I can define these two states, and since I have one terminal A, I will define one transition exclusively from S to B over A. This is what the meaning is of step 4. Next, 5. For each rule of the form x tends to W, add a transition from X to hash labeled W. So this we have already seen. So it is like for example x tends to A. So add a transition from X to hash labeled W. So this is almost like accepting the state, or sorry, accepting the string. So next step is, for each rule of the form x tends to epsilon, mark state X as accepting. So whenever we have x tends to epsilon, okay, if for example we had one particular rule or production like S tends to epsilon, so this is very much obvious that the start state of the machine or the start state of the grammar itself is the accepting state. So that is what the meaning is. We can simply mark state X here or S in this case as accepting state. So how to identify the accepting states? Any state with two concentric circles will be identified as accepting state. And finally, mark state hash as accepting. So this is the generic procedure to convert any given regular grammar to finite state machine. So we will take up one particular small example, even length strings. Again, we will take up the same example of even length strings. So we have seen the regular grammar productions or the rules defined. So as per the procedure, if we go as per the procedure, I will first list out capital V. So the procedure says identify each of the non-terminal as one of these state. So which are the non-terminal? It is only capital S, capital T, and terminal is only A and B. Okay. So I can define S as one state and T as another state. So this is my very basic step. Okay. Now when we look at this particular production, S tends to epsilon, this indicates that it is, the rule is of the form what x tends to epsilon. So it's obvious that I have to make that particular start state itself as the accepting state. So I have done that. So the start state itself becomes the final state or accepting states. The next production or the rule in the grammar is S tends to AT. So we have to identify the non-terminal here. So S and T, and the input symbol here is A. So from S to T, I need to define an explicit transition over the input symbol A. Similarly, it holds good even for the next rule or the production in the grammar. S tends to T, from S we can have a transition over T. So I can mention in the same transition as A comma B, which is valid. Next is T leads to A and T leads to B. Okay, I'll come back to this particular transition later. We will first take care of these two transitions. So T tends to AS. So again, there is involvement of two different states because two non-terminals exist here, capital T and capital S, and even in the next rule as well. So I can just write this. Okay. So whenever capital T tends to A and capital T tends to B, so this means that the string is by default accepted by the language. So this is the equivalent finite state machine. So there's one more example, the strings that end with 4A, and for this particular regular language we have to design a regular grammar which accepts all the strings which belong to A comma B star such that the string ends with the pattern 4A's. Okay, so it's not a pattern which exists in between the string, but it is a pattern which ends with this particular pattern. So this pattern appears only at the end of the string. So the regular grammar is like this. So it's we are very much sure, or we have ensured that 4A should be appearing. Okay, so before that, this is important. See, the string, it should end with 4A. This is important. This is given in the question. Okay, but before this particular pattern, I can have any sequence of B's and A's. Okay, and when the string appears before this particular pattern and that particular string can take any number of B's and any number of A's, then there is no constraint or restriction attached there. Okay, so in the process of defining the regular grammar, so we have to take care of this as well. So we can start defining this particular first rule. So S tends to AS. Okay, so now for this capital S, I can have one more A. Okay, now first start deriving only the pattern. So I can start with S tends to AS. Okay, and then if I want only 4A, then I can make use of the same production and I can define this again. For this S, I can define its equivalent transition. Similarly, I can continue the process. I will get 3A and one more S, and finally I will get 4A. Okay, and so on. Got it? So now I cannot have a production something like this. If at all I introduced S tends to epsilon, then the moment when I replace S with epsilon, definitely I have obtained my string, that is string of length 4, that is 4A, it is ending also with 4A, but it means that nothing is also accepted. So a string of length 0 is also accepted if I introduce this particular production. So this particular production cannot be part of this particular regular grammar for the given regular language. So I have to take care of not defining S tends to epsilon, which is very important and crucial. That is the reason what we can do is, as and when we substitute the start symbol of the grammar with one terminal A, we have to start replacing the another A with some non-terminal. So you can see here S tends to AB, B tends to AC, C tends to AD, and then finally D tends to A. So all these four transitions, four productions or the rules, they take care of deriving four string or string of 4 A's, which is exactly equal to the pattern. So now since we also looked the matter of the fact that the string can be preceded with any number of B's and A's, so B also should be taken into consideration, right? Because I can start with B. Only constraint is the string should end with 4A. So I will define one more production to generate any number of B's. Okay. So this particular rule or production can be used exclusively to generate any number of B's. Okay. Either in the beginning of the string or in the middle of the string. But at the end we cannot generate any number of B's because we have a very specific restriction. So it's very necessary and important for us to look the language, regular language from all the different perspective. Only then we can define the regular grammar correctly and accurately, rather than making some rules or productions defined just for the sake of satisfying few acceptable strings. It's always good that we think a lot of from different perspective. That is the reason again we have to think what is the condition given for the string generation and what is the condition which is not being given or mentioned explicitly in the question or in the regular language. So having seen this particular concept, so the grammar was defined. So once the grammar is there, then transforming the grammar into its equivalent finite state machine is also simple based on the particular procedure. So here the terminals are capital S, capital B, capital C and capital D. So you can see here S, B, C and D, okay, all are identified with one particular state, and there is one more state called as hash, which is the accepting state. So next, once we have defined these particular states, we have to look and consider each one of the rule and consider one after the other. So first is S tends to AS. So you can see here we can define the transition. There are two non-terminals here, capital S and capital S. So this is an indication that the state will have a self transition to itself. So since it is defined for A, we can define the self transition over A itself. Okay. Similarly, when we take up the next rule, the same thing is applicable. The state S is defined over itself on the input symbol B. So next, when we look from the third rule, S tends to AB. So here the state is changing. So there is a transition from one state to another. So on S, or when the machine is in start state S, on receiving input symbol A, we make a transition to state B. So this rule, okay, is transformed in the form of transition between two states S and B. Similarly, the next rule is B tends to AC. So now from B to C, we need to define one transition over A. So that is done. And next is again C tends to AD, that is also done. And the last one is D tends to A. So since we have to identify the final state as hash and enclose it with two concentric circle based on the procedure, so we will give an explicit final state here as well. So finally from D we can have a transition over A. So we can see here how for a given particular language we have generated the regular grammar and we have also designed or transformed a given regular grammar to its equivalent finite state machine. So this is another example. So one character missing. Okay, first we will take up this particular finite state machine first, and then we will go to the regular grammar in this case. So we have the start state, and this is the non-deterministic finite state machine for a language accepting one character missing. So definitely when we see the sigma, okay, sigma is A comma B comma C, okay. So nothing, okay, since the start state itself is the final state, definitely the set of strings which belong to the language comprises of epsilon, okay. Epsilon is present in the language. Now whenever there is a transition or whenever there is a state change from one state to another, you can see here from S to A, the transition is defined over the input symbol B and C. So here the missing input symbol or the missing sigma is A, correct. So similarly for the next transition, when there is a transition from S to capital B, okay, A and C is being defined, so missing letter here is B. There is no transition defined for input symbol B. Similarly here when we consider S and C, the input symbols which are considered for the transition is A and B and the missing letter is C, okay. And the same thing is being taken care with respect to these states as well, A, B and C. When it comes to capital A, capital B, capital C, you can see that a self transition is defined again with respect to the same input symbol. So you can read any number of B and C as long as the machine retains or stays in state A. That is what the meaning is, 0 or more occurrence. So even here A is missing, here B and C, okay. So this is the finite state machine for a language which accepts one character missing. So any string you take, okay, combination of characters you take, you have to see to it that there is one input symbol missing always. So epsilon is accepted, only BC should be accepted, then only AB should be accepted, and finally AC should be accepted, okay, AC. And finally the same sequence can be repeated any number of times, okay. And which are those strings which should not be accepted? Single A should not be accepted because here two input characters are missing, B and C, but the question or the regular language says that only one character should be missing. So this should not be accepted, single B should not be accepted, C should not be accepted, A, B, C should not be accepted because all three input symbols are present in the string, which violates the definition of the regular language. So when we have seen the design of the finite state machine, so now we will just have a look at the grammar, how exactly the grammar can be defined. So since the start state itself is the final state, we can have one explicit transition defined over the start symbol of the grammar, that is S tends to epsilon, okay, which is very simple to understand. Next, based on, okay, so as and when we have the states, okay, from S we have one transition over B and over C, okay. So S tends to BC and S tends to BA, okay, and S tends to small ca and S tends to small cb, okay. So from the start state, how many were transitions? So you have from start state two transitions leading to capital A, from the start state you have two transitions leading to capital B state, and from start state you have two transitions leading to capital C. So you will get almost 6 transitions here, okay. All those 6 transitions are transformed as its equivalent rule in the regular grammar. So it's S tends to AB, S tends to AC and so on, okay. And next, when we have capital A, capital B and capital C as the states, we have to define transition over it again. And now since we have a self transition means what? So both the non-terminals should be same. So you can see here A tends to BA, so here both the non-terminals are same. Similarly, A tends to CA and even 0 or more occurrence. So self transition means what? Clean start, clean closure. So we should not forget to include the rule or the production which says A tends to epsilon, which is very important. Similarly, B tends to AB, CB and B tends to epsilon, and the remaining 3 productions or the rules for capital C. So this is how, if we take up any one regular language, we can design its equivalent finite state machine as well as we can generate its equivalent regular grammar. Thank you. So, the outcome of today's class is the definition of regular grammar. What is the correspondence and relationship between the regular language, the finite state machine, regular expression and the regular grammar? And we saw one particular theorem, in fact, to see how to convert a given regular grammar to its equivalent finite state machine and vice versa. And we took up few examples to make it much more evident to understand the concepts. Thank you.